Thank you. Marco, thank you very much for the kind introduction. And it's a real honor for me to give today's Marvel lecture. I hope I could live up to the name of Marvel. Anyway, I'd like to thank Professor Nicola Mazzari for inviting me, although he's not here. Anyway, what I would like to share with you today is some recent work that we have done in the area of 2D, atomically thin 2D materials. In particular, the effects of interactions and topological band effects in affecting the properties of those materials. So as you probably all know, there have been a lot of interest in atomically thin 2D materials. One of the most well-known example is graphene, which is just a single layer of graphite. Then, of course, there are many other layer materials from which you could make atomically thin one layer or multi-layer samples. And many of the important work, in fact, are being done here at EPFL. And so among the zoo of 2D materials, you could make out of the transition metal dicarbonate systems. They can be both semiconducting and metallic. You can make it out of insulators like boron nitride and so on. So in today's talk, I will be mostly focused on graphene system, some system related to the transition metal dicarbonates, and then some work on black phosphorus and also some magnetic materials. So this is basically the outline of the talk. I will begin with a quite interesting counterintuitive phenomenon that we had discovered recently, which is so-called electron supercollimation in graphene and in other 2D direct fermion system by applying a 1D disorder potential to it. And then next I will talk about a discovery we make on graphene nanoribbons that actually can hold quite interesting topological phases, which lead to some interesting physics. And then I'm going to move to look at the photophysics of quasi-2D systems, in particular how enhanced many-body interaction in this system lead to interesting excitonic physics and optical responses. For example, you could have so-called massless exciton in this kind of systems. Because 2D materials so thin, environment and substrate effect turn out to be very important in affecting their properties. And they could change the optical response and also other response in the system, such as plasmons and magnetism. So I will talk about that a bit. And then if I have time, I'm going to talk about some really new unpublished work that we have done on how band topology in 2D material could actually completely alter the optical selection rules of 2D material from that of conventional semiconductors. So I hope I have time to go through them, but if not, I could just stop somewhere. So let me begin with the discussion of this phenomenon of electron supercollimation by a 1D disorder potential. So as you probably all know, the electronic structure of graphene is quite unique. For the low energy carriers, it has a linear band dispersion. And because the states are actually combinations of orbitals from both the A and B sublattices, we could describe the electronic states using a quantum number relating to the amplitude of those sublattice A and B pi orbitals. And we call that the pseudospin. And the pseudospin of the state is either aligned or anti-aligned to the wave vectors. And it describes the bonding character between the neighboring carbon atoms in the two sublattices that form graphene. It is this chirality of the graphene wave function which suppress backscattering and lead to a number of interesting properties of graphene. For example, Klein tunneling. Klein tunneling is a phenomena which says that if you have a potential barrier imposed on graphene, then you have carrier incident normal to the barrier, then you would have a 100% transmission independent of the width and the height of the barrier. It is this suppression of backscattering that could lead to the phenomena I talked to you immediately. And this has been actually shown experimentally. So the phenomenon is the following. If you have pristine graphene, then the electronic structure, as I mentioned, is like this. But if I say apply a 1D potential along the x direction, so the potential is fluctuating along the x direction, then because there's suppression of backscattering, the states that are moving along the kx direction will be totally unaffected. But the states that are moving away from that direction will be strongly scattered. And in fact, you do the calculation, say within DFT or tight binding, then what you find is the electronic structure near the K point, it actually, near the direct point here, actually look like a wedge. And if you form a wave packet within this wedge region, the region will depend on the intensity of the disorder. What you find is that wave packet will propagate undistorted and guided to move along the x direction independent of its initial motion. So let me illustrate this with one example. So here's a realization of a Gaussian random fluctuating potential. Suppose now I have a Gaussian wave package in pristine graphene, and I want to propagate it. Now, if there's no potential, no disorder potential, then the wave packet would spread, and say, if I start in the x direction, it would just move like that as a function of time. But in the presence of this 1D potential along the x direction, what one finds is that the wave packet remains Gaussian, unspreaded, and move along the x direction. And if you start a wave packet to move along, say, an angle from the x direction, without disorder, it would just look exactly the same because graphene is isotropic. But in this presence of this fluctuating potential, you actually have the wave packet to move along the x direction, remain Gaussian. There's a bit of a tail back there, which you cannot see very well. So this is very counterintuitive. You would expect to have a disorder potential, things would spread. And the physics behind this is really Anderson localization. If I call this angle, the angle K make from the fluctuating potential direction, one would find that if the wave is moving exactly along the x direction, there is no backscattering, there is no localization. But if it's moving at an angle from the x direction, then the wave will be localized. In fact, the localization length exponentially decreases with the angle. So what happens is that the waves going in those directions will be localized, and you have the packet moving along the x direction. So this is a physics that owes to the chiral character, the pseudospin character of the states. The disorder leads to Anderson localization for all waves except those propagating nearly exactly along the fluctuating direction. In fact, the more disordered, the better supercollimation you would have. And this phenomena is actually fundamental to the direct cone physics of the system. So it should also occur on the surface states of topological insulators and also certain photonic crystals where the waves, the electromagnetic wave also had this kind of pseudospin character. In fact, very recently, together with a colleague, a former student of mine, we looked at photons in photonic crystals. It's so exactly the same behavior. Now let me talk about topological phases in graphene nanoribbon. You take a piece of graphene, you cut it into a ribbon. If the width is an order of nanometer, then we call that a nanoribbon. And of course, you could cut it in different ways. And for example, this ribbon we call a zigzag nanoribbon because the edge has a zigzag shape. And a ribbon like this would have, we call it an armchair ribbon because of the shape of the edge. It turns out that this kind of ribbons are all semiconductors. They actually have some really novel electronic and magnetic properties. When we studied this 10 years ago, or more than 10 years ago, it really kind of a toy system, idealized structure from a theoretical point of view. But nowadays, there are actually a tremendous renewed interest experimentally in this kind of system because of the discovery of a bottom-up chemical synthesis way of making nearly perfect graphene nanoribbons. So nowadays, you could make almost perfect armchair or zigzag graphene nanoribbons with width in the order of a few nanometers and length in the order of hundreds of nanometers. And they can be synthesized in solution or on a surface. And this is through a precursor molecule method. In fact, it's pioneered by Roman Faso here in Switzerland. So what you do is you take some precursor molecule like this one, put it on the surface or in a solution, heat it up. Then the bromine atoms would boil off and the molecules would polymerize. And here, for this particular case, you have a perfect 7 armchair graphene nanoribbon because they are, we call it that way because they have 7 rows of carbon atoms forming this armchair graphene nanoribbon. If you start with a different molecule, then you could form a nanoribbon of different width. And in fact, if you start with a precursor molecule with dopants on it, then you could make a ribbon that are periodically doped. And for example, this kind of ribbon, in fact, has been made experimentally. And depending on what kind of starting molecule, you could also make shapes look like this. And very recently, for example, in Mike Cromie's group, we were able to make heterojunctions of nanoribbons of different width. So now let me take a bit of digression and talk about geometry and topology, and then come back to the graphene nanoribbons. As you all know, topology is a kind of a description of the global property of geometric objects, and those properties are preserved under continuous deformation and characterized by some invariance. So, for example, a ball in a cup is equivalent topologically, but a donut and a ball is not equivalent topologically. You cannot transform topologically inequivalent objects to each other. And in general, the topological phase of an object is classified by integer invariance. So it is really a global property of the object that you want to look at. Now, geometric properties such as curvature are local properties, but integrals over local properties in general may characterize the topological global topology of the object you're interested in. So a famous example is that for a two-dimensional compact surface, and the integral of the Gaussian curvature will give you characterized by an integer. Now, if I want to look at the topology of electronic states, because we have a crystal, the Brillouin zone is a compact object, and the role of local geometry, say curvature, is now taken by another quantity, quantum mechanical quantity. It's called the Berry connection. It's given by this expression, where U is the periodic part of the Bloch function of your band structure. So understanding the non-trivial topology of Bloch bands, in fact, has led to a deeper understanding of many phenomena in physics. For example, understanding protective boundary states, integer quantum Hall effect, new phases of matter, and so forth. So the Nobel Prize for last year was in fact given on this topic. Now, for 1D crystals, you could also have symmetry-protected topological phases, and that is characterized by the Berry phase that you pick up when you integrate across the Brillouin zone for all the occupied band of your 1D crystal. And that could be characterized by a number, an invariant. We call that a Z2 invariant. It could be 0 or 1. And that's given Z2 is defined by this relation where gamma is the Berry's phase that you pick up when you integrate across the 1D Brillouin zone. So what we find is that all graphene nanoribbons, in fact, with spatial symmetry, in fact, holds symmetry-protected topological phases. And because of the well-known Bloch boundary correspondence, if you go from one phase, which is trivial, to a non-trivial topological phase, right at the boundary, you have to have a boundary state. So that should lead to some interesting physics, because you could have segments of graphene nanoribbons of different topological phases. So let me just summarize some of our main findings. What we find is the graphene nanoribbons are in fact large gap topological insulators. They have a gap in the order of 1 electron volt. And that topological phase is not due to spin-orbit coupling. It's due to the particular electronic states in the Brillouin zone. It's protected by symmetry of the system. When Z2 is equal to 0, then the system is what we call trivial topologically, and then Z2 equal to 1 is trivial case. And there's another very interesting fact regarding to the fact that we're in 1D, is that this is invariant number, Z2 can in fact be changed when you change the different terminating unit cell for your ribbon. So let me illustrate that for you. It's quite interesting. So suppose I have a 7 armchair ribbon given by here, and this is the end. The shape look like that. When you take precursor molecules and make the ribbon, they would look exactly like that. So the commensurate unit cell in the bulk that is commensurate to this edge, this end, will be something like that. So Z2, you do the calculation, is equal to 1. But if you terminate your ribbon with this edge, then the commensurate unit cell in the bulk is in fact something look like this. If you do the calculation, you will find that Z2 is equal to 0. So this is very similar to the polyacetylene case. Depending on how you end the end, how you terminate the end, you could be in one of the two ground states. Okay. So that actually leads to some interesting physics. For example, if I look at a heterojunction between a 7 and a 5 armchair graphene nanoribbons, suppose I join them like this to form a junction look like that. Here's the interface. Then on the left, because of this n, the bulk unit cell is given like this, Z2 is equal to 1. On the right, the edge starts right here, the unit cell is given by this, and Z2 is equal to 1. So according to the analysis, then this two segment has the same topology, so there should not be any interface states between the two. In fact, if you do a DFT or even a GW calculation, you would find that there are no gap states at the junction, localized states at the junction in the gap. On the other hand, suppose I make the same interface with the same two segment, but just shift the right ribbon up by a little bit, so you form a more symmetric junction like this. Then on the left, nothing happens because I didn't do anything, so Z2 is equal to 1. On the right, on the other hand, the unit cell that you construct will have a shape look like this, and Z2 is equal to 0. So according to the bulk interface correspondence, then there should be an interface state at the junction. Indeed, if you do a GW calculation or DFT calculation, this is the interface state you find. So this is another example between a 9-7 junction. When I have a asymmetric junction, then there's no interface state. When I have a symmetric junction, there is a nice interface state. Very counterintuitive. You would expect actually an interface state in the more asymmetric junction. But this is not always the case, depending on what ribbon you look at. In fact, you could completely characterize and categorize the topological invariance of the nanoribbons. For example, here I give the explicit formulas for armchair nanoribbons, graphene with different width. And the Z2 invariant, in fact, depends on whether n is odd and how the system is terminated. And they're given explicitly by this expression, which you could derive analytically within a type binding model. So here, the bracket corresponds to the so-called floor function. So once you experimentally know what the shape of the ribbon is, you could deduce what the topological invariance. So let's look at an example of a n armchair nanoribbon in vacuum. Then it looks something like that. Z2 is equal to 1. Vacuum is trivial, so therefore you would expect n states here. These are the calculated n states. In fact, this has been seen experimentally because one could make this kind of ribbon now. Many times, here are two examples. This is clearly an n state seen in STM image, and this is done by Mike Cromie's group. So you have seen this, although it's never interpreted in terms of this kind of topological quantities. Even more interesting is that you could modify the topology of the system by doping. So for example, here I look at the case of a pristine 7 armchair graphene nanoribbon in junction with the periodically boron dope case, which I mentioned has already been synthesized experimentally. So what one find is that by doping the system, you introduce the dopant bands in the material, and those bands has a different Zach phase or Berry's phase, and so that it could modify the topological phase of the system. So here on the left, Z2 is equal to 1, and the right is Z2 is equal to 0, and that gives rise to a very localized interface state. Periodic doping can change the band topology very much, even though geometrically there's nothing changed here except some of the atoms are replaced by boron. it gives rise to a zero mid-gap localized states. And what's more interesting is that these states are very robust spin centers because the Coulomb U for adding another electron to that state is very large, in the order of half an electron volts. So they behave like spin centers. And if I have two junctions nearby, the states will couple antiferromantically with each other. So in principle, you could make a superlattice of this. Then you could have a very robust quantum spin 1/2 chain with tunable nearest neighbor coupling strength, because you could vary the distance between the junction. So here's one calculation we did for superlattice of pristine boron dimer dope and pristine and so on graphene nanoribbon. You see that there are junction states. These are not defect states. They are not associated with boron. These are actually at the junction due to the topological phase difference. And so schematically, the spins localized on the interface are antiferromantically coupled. They couple through either the pristine region or the boron dope region. And if you look at the coupling strength, say doing within the DFT plus U type of calculation, what you find is that the coupling strength decays exponentially with distance as you expected. What's interesting is that even though the spins are actually pretty far away, in the order of nanometers away, the exchange energy, in fact, is quite large, in the order of few millielectron volts. And this is because these are not atomic states, spin state. They are interface states that has a bit of extent, and therefore the coupling strength is quite large. So this is a pretty interesting new spin 1/2 chain that people, I think, could play with. In fact, you consider one of this kind of chain and put it on top of a superconductor, one would expect to find Majorana fermion end states on the chain. Just like you're putting atomic chains on the atomic spin chains on superconductors. Now let me turn to another topic. This is the photophysics of 2D systems. For example, boron nitride, molybdenum disulfide is very similar to graphene in terms of its symmetry, but it's a semiconductor. The low energy states are similar to graphene at the corner of the Brillouin zone. There's really, why people are interested in this system is that there are really very strong light-matter interactions between the system and the electromagnetic wave will lead to very interesting excitonic physics. And because of the large spin-orbit coupling, the spin texture of the states in, say, the K-prime valley is very different from that of the K valley. That lead to valley photodiachorism. That is, you could excite one valley using one circular polarized light and excite the other valley using opposite polarized light. So this kind of system allows you to have independent control of charge, spin, and the valley degree of freedom. So that's why people are very much excited about this kind of material. So before I show you some results on the photophysics of this material, let me say a few words about electron-electron and electron-hole interaction in reduced dimension. There are actually two very important effects that one should keep in mind. One is more well-known, which is the enhanced Coulomb interaction in reduced dimension. Another one, which is less well-known, is that there can be strong and very strange spatial screening dependence on the interaction in 2D materials. Here, I give you a schematic diagram. Suppose you have a 2D material and you have two charges here. If I look at the screening on the interaction between these two charges, then of course when they are very close to each other, there's no screening because the electrons can't get in between them. When they go further away, the screening kicks in, but when they're very far away, then you see that the field lines go outside of the sample because we still live in 3 dimensions, and then screening becomes ineffective again. So in fact, if you look at the effective dielectric function between the two particles, the screening the interaction between the two particles, one would find the following. In a bulk semiconductor, what you expect is epsilon as a function of the distance. A small distance is 1, and then quickly goes to a constant after a few bond lengths. But in 2D, what happens is that you start at 1, then it peaks, and then quickly decrease back to 1 again. And this distance over which it peaks is related, of course, to the thickness of the film of the material, and now we have atomically thin system. Another thing is that your sample has to live in some environment. For example, you put it in a substrate, then you see that the field line goes into the substrate. So this interaction is now can be strongly modified by the environmental screening of substrate. So let me show you a couple of results illustrating this kind of effects. Here is some earlier work that we did on the optical properties of a monolayer moly disulfide. These are calculations done through the so-called ab initio GW-beta salpeter equation approach. Basically, it's a many-body perturbation theory with no adjustable parameters into the calculations. So what's plotted here on the lower left is the band structure of moly disulfide. The blue line is the LDA calculation, Kongshan bands, and then the red line are the GW quasi-particle bands, where you include the electron self-energy effects. And the material's direct gap at the corner of the Brillouin zone, the top of the valence band is split due to spin-orbit interactions. So you see, in terms of an interband transition picture, you will see a number of transitions between the bands. On the top left here is the absorbance calculated as a function of photon energy. The red line here, it corresponds to taking the quasi-particle band structure, do the interband transition calculation, neglecting electron-hole interaction, and that's what you have. Now, when you include electron-hole interaction through this beta salpeter equation formalism, then you get something completely different. You have series of peaks and huge increase in the oscillator strength. These peaks actually correspond to a series of excitons arising from each of the interband transitions. So the A prime, A double prime correspond to various excitons due to this A transition, and so on. In fact, you could get huge excitonic states for this C transition here. So two things I would like you to note. One is that the exciton binding energies are huge, around 0.7 or 1 electron volt typically. And the oscillator strengths are now very large. Because of the strong electron-hole interaction, it robs all the optical oscillator strength from high frequency to low frequency. How's it compared to experiment? This is some work that's done by Tony Hines' group when he was still at Stanford. This is absorbance, absolute percent as a function of photon energy again. They see two peaks, A and B, which corresponds very well to the first two peaks here. And then there's a strong absorption at high frequency, which correspond to all this higher excited state of the excitons. In fact, we have forgotten one thing in our calculation. which is the electron-phonon interaction. You include that into the calculation, then you would broaden the high energy transitions, and you would get this curve, and now you will have a better agreement with experiment. One thing I would like to point out a bit more is that the absorbance of this material is really quite strong. A monolayer is only about 0.5 nanometer, but it could absorb in this frequency range about 20% or more of the light, just for a single atomic layer. And you could compare that to bilayer graphene, the absorbance would be around 5%, and for silicon with the same thickness, it would be around 0.02%. And even our predicted C excitons had recently been observed in resonant Raman scattering measurements. Now let's look at some of the details regarding to the excitonic states. They actually are very different from what you expect from a typical semiconductor. Here is our calculated result for the lowest energy exciton for the A transition, and then you have a lot of excited state ones. And some of them are optically bright, other ones are optically dark due to symmetry. And if you look at the wave function of the excitons, excitons are just a linear combination of 3 electron hole excitations. And from our calculation, you could get out this coefficient. And you plot it out, it gives you the wave function, the envelope wave function of the exciton in K-space. So here's a 1s, the lowest energy exciton, 2p, and 2s corresponding to those states. So you look at the wave function like this, you find that the amplitude is completely within about 2 or 3% of the Brillouin zone at the band extremum. So that means that in real space, these excitons, even though they have very large binding energy in the order of 1 volt, is very extended. It has extend about several nanometers, which are tens of interatomic distance. And if you try to understand the property of excitons in this kind of material using a kind of a hydrogenic model, that is, take the quasi-particle band structure, do a hydrogenic-like calculation with some screening that you adjust until you fit the lowest energy exciton. Then what you find is a spectrum like this, which is very, very different from that one, ab initio one. And the origin, the physical origin for that is this very strange spatial dependent screening that I talked to you about earlier. For the 1s state, the electron and hole kind of sit right on top of each other, so their separation is small, so they actually see a large screening. But you look at the 2s and 2p states, they are much further away, so they are in fact in this region, so screening is significantly reduced compared to the hydrogenic model. They actually are much strongly interacting with each other. And that's why it brings all those states down from this hydrogenic picture. And finally, the 2p state, in fact, has a larger extent than the 2s state, so that makes the 2p lower in energy than the 2s, which reverses what you expect in terms of the ordering of the states. So in fact, our predicted dark excitons and this reverse quantum level order have been seen experimentally by my colleague Xiang Zhang at Berkeley using 2-photon spectroscopy. Let me now turn to substrate screening, why it is very important. It can change the property of 2D material significantly. So here I give you an illustration of a monolayer molybdenum sitting on top of just a layer of graphene. If I put a point charge here and ask what is the induced electronic screening charge due to the fact that I have an extra layer of graphene, what you find that the induced charge look like this. It's quite complicated. And in order to get this right correctly, you really need to incorporate the whole full non-local dielectric screening effect into the system. And in fact, for some systems, having a substrate or encapsulated on top also with another inert layer, quote unquote, you could renormalize the property of your sample significant. You could change your gap by more than 50% and change the exciton binding energy by a factor of 2 or more. And also you could tune the plasmon property of the material. So let me give you one example. This is a case of black phosphorus. People are very excited about this material because a single layer of this black phosphorine has an optical gap of 1.5 eV, very nice. But the material is not stable in air. So what people typically do is encapsulate the material in some big gap insulating inert material, like on top of a sapphire substrate and cap it with layers of boron nitride. The hope is then the property of the material still remain more or less intact. What we find is that's not true. You actually change the material property strongly. So here is our calculated result of a few layers of black phosphorus, 1, 2, 3, 4, on top of sapphire, capped by 15 layers of boron nitride. This is the isolated sample calculation, quasi-particle gap, optical transition, the exciton binding energy for the lowest exciton. Here is the calculated results with the capped layer. In the interest of time, let me just focus on the monolayer case because the effect is strongest there. What you see that is that the quasi-particle gap, the band gap, in fact is renormalized by almost half an electron volt, just being on top of a big gap insulator. And the exciton binding energy with the capping changed by a factor of 3. And the effects for the other thicker layer, it has a similar trend but smaller. And this is a very important lesson to learn when somebody tell you the property of the measure 2D material, you should ask what environment that material is in. Another very interesting effect that we find is regarding to the dispersion of excitons in this system. So far, because we're only looking at optical spectroscopy, we look at excitons with Q going to 0. But of course, Q not equal to 0 excitons exist. You could measure it using different techniques, and they're very important in understanding other properties like exciton dynamics. For normal conventional semiconductor, you would expect that the dispersion relation of the exciton as a function of the center mass momentum would go like Q squared over some mass, where the mass would be the electron mass plus the whole mass. However, in 2D, there are certain branches of exciton that this relation is completely not true, which is a very surprising result that people have not realized before. And the origin of this is actually come from a many-body effect. The electron-hole interaction kernel, in fact, has 2 turns if you look at it carefully. There's a direct turn that involves the attractive screen interaction between the electron and hole. That's what you normally think about from a textbook point of view. But there's also an exchange interaction between the electron and hole, which is repulsive and involves the big Coulomb interaction. And it is this turn going to lead to some very interesting physics. So here's a calculation we did for moly disulfide exciton dispersion. So here is the excited state of the excitons. This is ground state as a function of momentum for the A series that I mentioned. The blue lines correspond to the spin and spin flip transition. The red lines correspond to spin directly transition without flipping the spin. So the optically active one is the so-called light spin transition. It turns out that this exchange term only applies to light spin transitions. So only apply to the optically active states. So you see for the optically active states, they don't behave like parabolic bands. And in fact, for this particular branch of exciton, it has a linear dispersion. The velocity of the exciton is about 10 to the minus 3 of the velocity of light. So this is a very interesting new result. The linear dispersion relation comes from the exchange term, comes from the form of the Coulomb interaction in 2 dimensions. So it should exist in all atomically thin semiconductors. And in fact, you have for this kind of TMD materials, the low energy excitations on 2 valley, K and K prime. This exchange term, in fact, couple the 2 set of excitons. And the excitons now are linear combination of excitons from the 2 valleys. And they have a relative phase, and that phase depends on the center mass momentum. And if you look at Q go around Q equal to 0, it has a winding number of 2, and that qualitatively changes the photo response of the system. But I don't have time to talk about it today. You could ask me about that later if you're interested. Another consequence of screening is that you could also have very interesting screening or substrate effects on the plasmons of the system. Some of the TMDs are metallic, like niobium diselenide and so on. They would support intrinsic plasmons, but those plasmons, in fact, don't behave like 2D electron plasmons, classical ones. Classical ones, you would think it should go like square root of the Q dispersion. What one finds in 2D is that at small q, it does behave like square root of the q, right about here. But it flattens out at large q, square root of the q would go like that. And it's qualitatively different from that of ideal 2D system. And that is, in fact, due to interband transition screening. Even more interesting is that if you put the metallic 2D crystals on a substrate, then the plasmon dispersion can be changed very much. Here is a result that we have with looking at the plasmon of tantalum diselenide on isolated but on different substrates, like, for example, a monolayer tungsten diselenide or 2-layer or boron nitride. And you see that you can modify the dispersion and energy of the plasma by as much as 20–30%. So this effect is very large and can have significant kind of interesting applications. Now, what about magnetism in this kind of material? So far, we looked at optics and the electronic properties. The question is, when you're down to one monolayer, can you have a magnetism like ferromagnetism in this kind of material? In principle, you should be able to have it. And people have looked at thin film magnets. And there you really need, because of the Merman-Wagner theorem, you need to have some kind of anisotropy in order to have for ferromagnetism to occur. So very recently, together with some experimental group at Berkeley and Irvine, we look at this particular system, chromium germanium telluride. You could thin it down to a few monolayer. And what we find is, indeed, ferromagnetism can exist all the way down to 1 or 2 layers. The experiments are done through scanning magneto Kirk microscopy. And the theory we did for understanding magnetism in this materials use renormalized spin wave formalism. And because of limited time, I just say a few things about what we find. One is, of course, TC is suppressed as you go to thinner layer. That's not surprising. Something that we find, which is very surprising and can potentially be very useful, is that you could tune the magnetism of this material with a small external electric field. And the reason for that, well, let me skip this. This just explains why TC decreases with layer. The reason why is that if you look at the transition temperature, the magnetic transition temperature of a 2D material, it's dominated by anisotropy. You will not have magnetism if there's no anisotropic interaction. And that comes from usually spin-orbit coupling, and it's very small compared to in 3 dimension where TC is determined by exchange interaction, which is very large, usually in the order of a few hundred Tesla in that unit. So what we find is that if you look at this system and at different thickness, by applying a very small magnetic field to the system, you could enhance the anisotropy of the system, and you could dramatically change the transition temperature. So that gives you another degree to tune the magnetism of the system. For illustration, Bloch system, there's hardly any change when you apply a field up to about 1 Tesla. But when you're down to 2 or 3 layers, you see that by applying a small field, you could tune the transition temperature significantly. And the blue dots are experimental data from my colleagues, and the red curve are the theoretical calculated TC using a renormalized spin wave theory. I see that I'm running out of time, so I have one topic, but I will just briefly tell you what the physics is, and then if people are interested, they could ask me more. We have been looking at the optical transition of semiconductor in 2 dimensions. So before we talk about something new related to that, let's look at conventional semiconductors. The conventional semiconductors, you look in the textbook, you will find the following selection rule, that for dipole-allowed systems, the optically active excitons are S-like, and for dipole-forbidden system, the active excitons are P-like. And that you could look up the physics in a standard textbook. What we find in 2D material system is that many of this system has an extra degree of freedom, this pseudospin, describing the multi-orbital physics of the system. And because in 2 dimension, this kind of pseudospin, when it goes around in K-space, it could have a winding number. In 3 dimension, that's hard to find. In 2 dimension, you have a winding number. And the winding number, in fact, changes the optical selection rule of the system. Here is a bilayer graphene in the electric field. It's a semiconductor. The pseudospin of the electron goes like that. What we find is then that you could have a new set of selection rules. The you will have 0 optical transition unless that the angular momentum quantum number of the exciton is equal to the winding number of the interband transition matrix elements. And that leads to some very interesting physics. For example, let me skip that. For example, if you look at the bilayer graphene in the electric field, which has a gap, then instead, this is a dipole allowed system, so you expect the S exciton to be bright, the P exciton to be forbidden, but you actually have the opposite. The P light one is very bright, the S light one is very weak, and that's due to this winding number of the electronic state, topological effect. And this, in fact, has been measured very recently by Paul McEwen's group in collaboration with us. And you see that you put in different magnetic electric field, the gap opens up more, and then you have an S state, which is very weak, but the P state is very strong. So let me stop here. Here's a summary. I hope I have conveyed to you that atomically thin 2D materials are different, and they potentially can be very useful. And they have many interesting new properties, and that can be tuned by the environment. And before I stop, let me acknowledge my collaborators. All the work was done by my outstanding graduate students and postdocs. Their names listed here. And these are my senior experimental collaborator at Berkeley and Paul McEwen at Cornell. And our work is supported by the Department of Energy, National Science Foundation, and the Office of Naval Research. Thank you very much for your attention. I'm sorry I'm running over a bit.